Hello everyone, my name is Greg Ristabin from Olympus NDT. I'd like to welcome everyone today to this webinar on stress corrosion cracking inspection using eddy current array as an alternative to traditional NDT methods. This webinar will include an overview of the exciting new eddy current array solution for the detection of stress corrosion cracking in refinery process piping using the new user-friendly MXE software with the OmniScan MX flaw detector. Our presenter today is Tommy Borgila. Tommy has worked for the Olympus NDT for 13 years and is the product manager for the entire eddy current testing and bond testing line of products. This webinar should last about an hour. If you have questions, please type them into the Q&A panel in the lower right portion of your screen. If we don't get to your questions during the course of the presentation, the questions will be addressed personally either by email or by phone after the event is over. The presentation, along with the Q&A, will be archived on our website at www.olympus-ims.com. Now, without further ado, I'd like to turn the presentation over to Tommy Borgila. Tommy, it's all yours.
All right, thank you, Greg, and good day, everybody. Thank you for attending this eddy current array webinar. We are going to spend less than 1 hour together. It's mostly a PowerPoint presentation with a bit of live demonstration near the end of this presentation. So this webinar is about a new eddy current array solution that was released by Olympus on October the 1st of this year. It's dedicated to process piping, refinery, fertilizer plants, focusing on detection of surface breaking defects such as stress corrosion cracking. Obviously, being an eddy current solution, it has to be applied to a conductive metal material, so it's applied to metallic piping, and we're talking of mainly stainless steels and also working on carbon steel. So today we are going to review the eddy current array technology. We're going to see the benefits of ECA as general and benefits of the SCC solution. We are going to see the advantages over penetrant testing, an explanation of the inspection method of ECA, and we're going to have an actual demonstration demonstrating the calibration steps, a quick inspection procedure, and how to interpret the results with the OmniScan MX. We're going to conclude this presentation with a couple actual SCC examples. Eddy current array is basically multiple eddy current coils, whether etched or manually wound, being switched electronically, as opposed to a manual scan to cover a surface with a tiny single coil. So my favorite saying these days is that eddy current array is eddy current for the reason that it's basically the same technology with obviously a couple differences, but it should be used the same. The way to calibrate the instrument, the performance, and the detection capabilities are very similar. Eddy current array is employing eddy current technology. It's using the same physics, most of the times the same coils. However, it allows faster large surface scanning. It allows color imagery created from all the coils being read all together, and it improves the probability of detection as opposed to somebody scrubbing a surface with a tiny coil looking for small size defects. Explaining eddy current array is much easier when it's starting from eddy current. So back to eddy current 101. The magnetic coupling, basically the distance from the probe coil to the test surface, is called the liftoff. And that property of being able to detect defects from a little distance is very interesting. It allows inspecting on conductive test pieces, stainless steels, aluminum, carbon steels, to name the most used in this industry. and it's basically also a surface inspection technology as opposed to ultrasound, which is a volumetric inspection technology. The magnetic coupling or the ability for editor-end testing to detect defects without being in contact with the surface, but just in close vicinity, makes it possible to have a very minimal surface preparation. Only to clean the surface, making sure the probe does not wobble too much is necessary. The magnetic coupling has this advantage that it allows inspecting through the paint, and we're talking of paint thicknesses about 1 millimeter or 40 thou on ferromagnetic materials like carbon steel, ferritic stainless steels, and about half of that, so half a millimeter or 20 thou on austenitic stainless steel. The detection and inspection procedure is as good as the calibration standard. So it's very important to have the same material type and with known defects on it to be able to calibrate, just like with editor-end testing. Editor-end array, if I use one of the most known in the industry, one of the most known probes in the industry, a conventional absolute probe, pencil probe, and basically apply that to an array, 32 times this same probe, we would have basically the same basic wiring, except that the different coils get activated on different times very, very fast by the electronic switcher, and it's called the multiplexer. So all those switching intervals are actually called the time slots. So the time slots are the intervals where each of the coils get read. That's as far as this explanation will get, because we only need in this webinar knowing that it's electronic scan without going into more details. So the representation of eddy current array is basically an impedance plane working with the same representation as typical eddy current, displaying in this case 32 channels, and basically out of the 32 channels in the impedance plane, we're building a C-scan display. So this axis on the horizontal is the time or distance. This axis gets populated as you scan, basically. And time or distance means if the probe gets encoded with a position encoder, position recorder, that's no longer a time-based scan, but an encoded scan. The vertical axis of the C-scan is displaying the channels, and starting from the bottom, typically the channel number 1 is the lower, and the most channels is displayed at the top. Well, with 32 channels, we would have an arrangement like this, and that is called the probe coverage. The interval between two channels is called the probe resolution. So, how are these colors appearing? Certainly not magically. So we're taking the vertical position of each of those signals on the impedance plane and translating that vertical amplitude as a color palette. So for instance, all of the signals lower than that red line there on the left are represented as shades of gray. And as most of the C-scan display actually has no defect on that area, we basically do have a gray background signal with only a couple indications in there. So as soon as the signals get into the alarm zone, the red zone there, we actually get an indication because the equipment does process the signals and display anything going into the alarm box as a different color. That makes it very easy for distinguishing between go signals, like this indication number 1 that is smaller than the box, as opposed to the rejected signals, like these 3. One interesting aspect of eddy current array is its ability to evaluate defect depth. One of the first factors influencing the amplitude changes is the depth of a defect, and I'm speaking of a surface braiding defect. So the amplitude translates to colors in the C-scan. Therefore, the color is a representation of the depth when calibrated properly. So it's possible to set up the instrument easily to display different colors for different depths. Eddy current array, as conventional eddy current technology, will provide valuable information on a flood depth within, of course, the limits of eddy current capabilities. And eddy current penetration really goes up to 2 to 4 millimeter. I wrote 3 to 4. That's typical, the maximum reach of eddy current. So it's not fair to say that eddy current will be able to detect up to ½ inch. At least not the eddy current we're talking about in this solution. The eddy current array has this advantage of allowing a very quick distinction of the defect depth from the C-scan color, or analysis of the impedance plane if somebody wants to. It takes longer and you can get a more thorough analysis, but it's possible to do. So for example, you can distinguish from a 0.5 mm deep, a 1 mm, or a 2 millimeter, as they have different colors. And that's precisely what this example is showing right now. That's an actual stress corrosion cracking pipe being scanned with eddy current array showing different depths. It can also be configured as a go, no-go. So we have this nice color palette here looking like a penetrant testing scan. Basically, what's white is good, what's red is bad. It's as easy as that. And when taking that cursor in analysis mode, it's going to display the impedance view and the strip chart. So for an eddy current analyst, that's going to mean something, and he's going to be able to identify and tag those defects accordingly. The benefits of eddy current array technology as a whole. So eddy current array as ECT allows inspection through paint or thin coatings. It provides a large coverage coming from the probe length, very fast scanning, color imagery, easy archiving and analysis. Defect depth evaluation is also possible. Now, this section is about the SCC process pipe ECA solution specific to that solution. So it is using the OmniScan MX with ECA module, the eddy current array module, the blue one, with a new software that we just released. Olympus put that on the website as October the 1st of this year, and it's a very different in some ways software because it's so much easier to use. It can be used like eddy current testing conventional. So people typically don't believe how easy it is when they realize it can be operated just like a Nortec 500 and do eddy current array scans with it. It's also using a new pipe kit ECA probe with an encoder that we see on the picture. It's using a special purpose calibration standard that should be made of the same material to inspect. And as an optional accessory, a set of plastic or paper shims just to simulate the proper paint thickness. The probe, based on the Olympus Flex array, so it's a flexible probe, and it is mounted on what we call a wedge, which is nothing more than a piece of plastic, just to fit the various pipe diameters. We offer that in the pipe kit. So the SCC process pipe solution is called, the probe that comes with it is called the pipe kit, and we offer 15 of them wedges just to cover any diameter from 1.3 inches, which is 33.4, I believe, millimeters, up to flat. So the last wedge is 48 inches, and from 48 inches to flat, there's not enough curvature, so we decided let's just go with the flat one as a large diameter. The wedges can be changed very easily. It takes about 1 minute and a roll of Teflon tape. That's not shown on the picture, but it's the most important accessory here because it prevents your probe from being damaged when scanning. So it's important to remove that tape, remove the wedge, put the new one in, and get the Teflon tape back again. as an optional additional equipment, Olympus happily supplies paint thickness measurement probes, the NEC 2236 model that can work with the Nortec 500 or the OmniScan EdiTrend array or EdiTrend testing module. The same OmniScan can do EdiTrend conventional and EdiTrend array, as seen on the picture below, with a proper cable, of course, and a set of thickness plastic shims. It's outside the goal of this presentation to explain this method of measuring the paint thickness, but Olympus can happily supply you with more information on the same if you type those in the Q&A of this webinar. Benefits of this process pipe solution. It is a very efficient inspection covering 2 inches in one single scan. And obviously, from the wedge diameters, it is understood that we're standing along the axis of the pipes or tubes. Well, you could actually scan in both directions, but it's probably more efficient to scan along the axis. It's a very portable solution. It works on ferromagnetic or non-ferromagnetic alloys. The indications will be detected in all orientations, and that's very important because we do not want to restrict or hide defects as we're scanning. Probably the most important advantage here, is there's no need for removing the paint. EdiTrend array will work through the paint. The defect depth evaluation is possible, obviously within the reach of EdiTrends. The solution can be quickly adaptable to diameters from 1.3 inches and up, very easily adapted, and providing encoded scans, easy archiving, and last but not the least, that's becoming a concern in the industry a lot more these days, it's a green method, and it's also lean compliant because it's a one-step inspection. There's no need for several persons in the process, but only the EdiTrend array inspector or EdiTrend inspector. So, speaking about paint removal, throughout this presentation, I refer to traditional NDT methods. With this solution in particular, the SCC solution, I am pointing to the penetrant testing a lot more than the magnetic particle because it applies a lot, EdiTrend array applies to replacing this method. So penetrant testing requires extensive surface preparation, the paint removal, the cleaning, anyway, all the pre-cleaning, post-cleaning. While ECA can detect and provide flaw depth information, so it does more than the PT and without removing the paint. So that little drawing there is just to show that the paint is just lift off for EdiTrend. Dirty tracks made some people laugh, as I heard. PT works as long as the tracks are clean and allow the penetrant to work. If anything falls in those tracks, the penetrant testing will have a hard time revealing the tracks, whereas it's still a discontinuity, so EdiTrend or EdiTrend array will still detect those tracks, even though they are full of grease or previous penetrant testing done on it or anything. Archiving. The OmniScan MX ECA allows easy archiving. There's actually a save key on the front of the instrument that allows to instantly save a file, and you actually get 2 files when you hit save. You get a bitmap and you get the actual file all together, so you can't mess up your archiving. So saving the data makes it easier to review the analysis, so basically play with the cursors, and that's exactly what this gentleman on the right is doing right now. So he's playing with the OmniScan while looking at other bitmaps on his computer coming from the compact flash that's on the OmniScan. So that's the way to exchange files with a computer. The report is out of the OmniScan. There's a single key press to produce that report. We're going to demonstrate that a little bit later on, but it's basically using the whatever's on screen and creating a quick report out of it. Post-process analysis was worth explaining. So as soon as somebody hits save and save an edit array file on the OmniScan, it becomes possible to review that file, reload it, and explore any part of the CScan with the cursors. And most important, it's possible to correct, if needed be, the settings. So we could think of probably the most common setting to correct will be the gain, to reveal more or less defects depending on the customer needs, or to change the color representation. That would be one of the most used cases where somebody would like to tune the results in analysis. And that can all be done on site or in the comfort of an office, reloading the data one after the other. So as opposed to penetrant testing or magnetic particle, it's a lot easier archiving, as basically scan and save, scan and save. Edit array provides major time savings when compared to penetrant testing. We're talking of 10 to 1 and up, and the end up goes up when PT goes wrong. Basically, it's if PT goes well and it's cleaned and it's cleaned properly and it works right away, there's no need to retest. That's a 10 to 1 saving. But if something happens and somebody has to reinspect, or it was not cleaned properly, well, the time required to do the penetrant testing goes a lot longer, quicker. So there's the direct cost of the penetrant testing being very low, if I follow my slides order here, but there's a lot of hidden cost, I would say. The paint removal is certainly one, the cleaning time, the dwell time, the post-cleaning, and if it's magnetic particle, there would be the demag part. There's a possible reinspection that has to be managed, and there's also the reapplication of the paint or coating. So edit array is a one-step inspection that gets rid of a lot of these problems. It's a lean and green approach. ECA is a one-step inspection that gets to scan large surfaces within minutes, does not require any particular preparation, provides instant results. Archiving and analysis also allow a very good ISO compliance, because it's possible to easily archive anything without much effort. Last but not the least here, coming more and more a concern in the industry, there are no chemicals involved, such as reapplication of the paint or waste disposal of those penetrant soaked towels. So ECA is a much greener method. Speaking of penetrant testing, the Olympus OmniScan MX ECA with the MXE 3.0 new software has now a set of representation to mimic the traditional views or traditional look of the traditional NDT method. So here's the penetrant testing red dye, and obviously the scans below are not from the parts up there. Those parts were actually taken from the internet with no link of the scans. I used the screenshots from a stress corrosion cracking pipe, and it's always the same pipe that you see scanned at the bottom of the pages. So same pipe at the bottom, but different parts at top, just to show the different colors. That's the only goal of this slide. That's the fluorescent penetrant testing, white contrast magnetic particle effect, and fluorescent magnetic particle. So it's easily changed in the OmniScan to select the appropriate palette to display the results, just like somebody is used to see them with a traditional NDT method. Building a chart of all the good pros and cons for the traditional NDT methods against ECA, or ECA against those methods. Edit array is a lot simpler to use as years before, and now with the new MHC 3.0 software that is used like in the ECT flaw detector. But I think the win goes to the penetrant testing and magnetic particle, for they are definitely easier to use than an edit equipment, as simpler as it gets. So PT wins here, but it stops there. So eddy current array requires minimal surface preparation or no demagnetization or post-cleaning. And obviously the traditional method needs very clean, very dry surface, need the paint to be removed, the coating if there's a small coating stripped. So ECA clearly wins. Eddy current array is not affected by weather conditions, apart maybe from a ECT or ECA inspector being not so happy to work in the rain, but there's no reason why the technology would not work. It's those equipment are really performant equipment and field ready. So penetrant testing and magnetic particle definitely require a lot more preparation if the conditions are not that easy. So if it's raining, it needs to be dried. So a tent needs to be built and all kind of preparation. Eddy current array is a green method, and we can't say that out of the traditional NDT methods. The paint removal, the reapplication, the waste disposal are all issues that the industry would be keen on getting rid of. And the list goes on. Eddy current array allows a reject criteria to be tuned, whether it's relevant or non-relevant indication, simply as playing with the gain live on the field, in the field while scanning or in post-process. PT and MP, I wrote indications only and no reject criteria. This is half true because it's still possible to tune the sensitivity, but certainly not as easily as eddy current array or as with any fine steps as eddy current array. Eddy current array provides excellent probability of detection, POD, on large surfaces and dirty cracks, yes, while PT or MP are highly dependent on the surface preparation and crack cleanliness. Eddy current array provides instant results, rapid coverage of large areas, so it's a highly productive method. PT/MP require pre-post planing, the demag, the dwell time, basically a much longer process. Eddy current array has this ability to display encoded scans. It creates imagery in the archiving and has the post-process analysis capability, which is just not there with the traditional methods. The equipment used now on that solution, the OmniScan MX flaw detector, plus the pipe kit that we call the SCC probe that gets you a flex array and a set of wedges and an encoder, a standard calibration standard, a standard practice. Olympus does already have some recommended instructions as far as how to set up, plus not an ECA inspector, but a certified eddy current testing inspector. So the same person that operates that Nortec for any duties can be using the OmniScan eddy current array flaw detector without being too much lost. As an overview of the steps that this person has to do from A to Z. A is the arrival on site and Z is the report. Well, obviously I didn't write it, but minimal surface preparation would count for basically wiping the pipe surface, making sure there's no bird drops or anything that would prevent the probe from scanning smoothly. But it's as far as it goes. So the calibration involves having the proper paint thickness on the standard, and if needed, it's always possible to measure that with ECT. So the same instrument could do both, the paint thickness check and the actual inspection. Fine-tuning as needed and a selection of the method, we are going to see that. And that's it, it's ready to inspect. So the actual inspection allows to save all scans, allow a very thorough archiving, or saving only the indications found. So if nothing is found, no need to save. That's the new continuous mode of the OmniScan. Optional analysis and review of indications. So if there's a need to tweak anything, it's possible to do it with the OmniScan. If there's no need because everybody's happy with the results, it's possible to go directly to the reporting phase. So, in details, the calibration refers to using a standard with known depth notches made of the same material to be inspected. It's recommended to put the proper paint thickness shim on, whether it's plastic or paper, and then follow the steps to perform the calibration, which I'm going to do in a minute. When I do the live demonstration very shortly, I'm actually going to use the same exact parts as you get to see there, so the same standard. I have two of them, one made of stainless steel 316 and one made of carbon steel, and I'm going to be using the same exact probe and paper shim. So if the paint thickness is unknown, here's an overview of what can be done using the proper probe, the NEC probe we talked earlier. And if you want, we can happily provide you with the procedure on how to determine the proper paint thickness using either a Nortec or an OmniScan instrument. So, the entire goal of the calibration step with ECA is to tune the parameters correctly, of course, and to obtain different colors for the different depths of the defect. So, in that example, I have 4 flaws. A short to a long one, and the shorter is less deep anyway. So it's the display was tuned to have 4 different colors. Or it's possible to select from 2 methods. Either you display the colors for the depth, or it can be configured as a go, no-go based on a specific flaw that is agreed with the end customer to be detected, and a smaller flaw not to be detected, for instance. We're going to see both methods in the demo. The analysis and reporting, using the cursor, changing sensitivity or display style, and producing the report as the last step, and we are also going to see that in a minute following the calibration steps. That is about time for demonstrating this eddy current array technology. So for good and bad news, you get to see the screen easily on this webinar, but you don't get to see what I am doing. So I'm going to describe as much as possible what I am doing with the probe, and try to imagine a guy in an office having an OmniScan and a probe in a large pipe just behind his chair, and that's the piece of pipe I'm going to be scanning shortly. So let's begin this presentation, and you should see in a minute the OmniScan screen. All right, so I'm going to start this presentation with the probe on the stainless steel 316 standard. So right now I'm having the probe with the encoder attached with a flat wedge on it, and I just put the probe on the standard with the shim on, and I'm basically going to null the instrument. So that says balancing. It's basically calculating the good material, and then what I'm doing is I'm lifting that probe up, so up and back on the standard, and there's a kind of display erase on the screen so the display doesn't get too crowded. That's why we lose the signal once in a while. But what you get to see there is the 32 traces, the 32 coils all together in the same impedance plane, to be basically shown just like conventional eddy current. So the idea here, while we're producing that liftoff, so I'm actually tapping the probe against the sample, that's generating liftoff from the cross there, that's the null point, to the air, which goes right now outside the screen. What I need to do is set that rotation angle. So my liftoff is going to look flat, and when we say flat, it means going to the left. So any eddy current knowledgeable person will be used to perform that step to set up the liftoff. Many instruments like the Nortec 500, they have an auto liftoff feature that allows to do that automatically. OmniScan does not have that, but it's very easily done, as you saw with the rotation knob, the rotation control. So once I have that liftoff, I'm ready to scan. So right now I'm scanning across my standard. I did not scan just yet. And we can see defects going up. Those are the EDM notches. I just keep rescanning. That's what you get to see there over and over, so you get to see something. And actually, I want those notches to fill the screen vertically, because this is what we are going to represent on the C-scan. Right now, this view is magnifying the impedance plane just for the sake of simplicity and explanation, but it's not the typical view we use all the time. We obviously want to use the C-scan view. But right now, I'm still in the eddy current principles, so still in step 1 of calibrating, making sure my signals fill that screen. All right, that's much better. So I start to have eddy current looking like signals, but 32 of them, because my probe has 32 channels. So I would be ready to switch to the C-scan display, except I'm not going to switch to it, and I'm going to show you the results on a carbon steel now. So the sample is identical. I'm going to explain a little bit in detail once I have the C-scan view, but I basically have a long notch and a few smaller notches. So I'm going to move to that carbon steel standard here, get rid of the vertical gain, otherwise I'll get lost if I don't, and re-null the system. And here comes my liftoff again, which has a clearly different angle as opposed to the stainless steel. So what I need to do is set up that angle, that liftoff angle, to be flat, something like this, seems proper, and going to the left also. On carbon steel, those notches are naturally oriented on the first quadrant, so going to top right. So what I like doing is moving my null point right in the middle, but keeping it lower on the vertical, so I get to see the defects a little bit better on carbon steel. I'm going to add some vertical gain. So I'm nulling the probe, scanning the standard, and pretty much the screen gets filled. That's all I needed. That's the way I would set a typical surface probe on an Nortec instrument, so that's the same way to set up an eddy current array probe on an OmniScan. Step number 2, activate the C-scan. So I leave the EC settings menu, and I'll be going into display menu and change that layout for what's called a CSI layout, strip chart, C-scan, strip chart, and impedance plane. And now I do have a C-scan layout that comes live. So we can see the wide notch and 5 of them smaller notches. This is the time-based C-scan, although it's possible to scan like this, so I could actually be ready for inspection if I wanted to. I will rather go and activate the step number 3, well, perform the step number 3, which is activating my encoder. So there's an on and off switch here from time to encoder. It takes a while to realize it's activated. All right. And I basically have encoded scan, so as I move back and forth, I do have recording. It is kind of rough. It needs some fine-tuning, so I'm going to go in encoder. For one thing, it was inverted, so I'm not going to explain why here. The scan end, I'm going to make it a shorter distance, just to magnify that C-scan view and resolution. I typically don't play with it except for that very application, the SCC. I prefer 0.3 mm resolution. I think it works a lot better, much cleaner images. So that's basically the kind of display you get while scanning the standard. I like to work with the continuous mode. It's a new mode the MXC 3.0 offers. The reason is I can scan continuously over and over without having to touch any single reset encoder key. So I can keep scanning endlessly until I'm tired or the job is done. And that's a lot, I think that's a lot easier to use. So I'm going to use that mode from now on with that webinar. So that takes care of step number 2. Let's go back to number 3, actually activating the encoder. So that was a calibration. Now we get into the fine-tuning phase. Although I could be ready just like that, I've got detection. It's good to have the proper detection, so I may want to lower the gain just a little bit to try to get a different contrast for the different defects. So I'm going to actually lower gain and rescan that standard, the same standard, trying to get different colors for the 3 different defects. Actually, what I want to do, what I'm trying to achieve is 3 very distinct colors here. And that gets better. So I forgot, but I'm going to scan with a shorter distance. That should improve on these display just a little bit. So what I did is I just magnified the results a little bit more. Yeah, that was too much. Sorry about that. Okay, let's get back to EC settings and keep on tuning that gain until I get 3 colors for the 3 first defects. I have a 0.5 mm. That's the wide notch. I don't care. All elements are working. That's good. That's the first notch. That's the 0.5 mm. I've got the 1 mm, and I do have 2 mm. So all the other ones are deeper, 3 and 4 mm. They're just going to show like the 2. So we're set up for 2 and up to show on the same color. 2 mm and deeper will show in pink shades. So at that point, I've got the choice to scan start scanning, which I'm going to do in a minute, and I can choose to display the results either as a depth information or as a go no go. So I'm going to do a little bit of both using the actual standard, the actual pipe. So I'm going to try not to disconnect myself here and turn to that piece of pipe. So I'm not changing the wedge. I'm rather going to do some circumferential scans just for the sake of not taking too much of your time on this webinar, trying to change my wedge here. Anyway, so I'm about ready. So I'm going to null on a good part on the pipe, a part I know was good before I scanned it before. And that's my actual pipe. Gets a little bit more noisy than the calibration standard. So here's a stress corrosion cracking colony. We actually got 2, one on the very left and the major one on the right. And you get to see the different depths of those defects. So the red ones are 1 or 2 millimeter, depending if it's red or pink. They are 1 and 2 millimeters and up, possibly. The green one was about 1 millimeter. The blue was about 0.5. So it gets you a very clear picture of what is the depth of those defects. And the shape cannot be mistaken. It's definitely an SCC colony. So at that point, I could save those signals. So if I hit the Save key on the front panel of the OmniScan, it's going to dump and generate a file, a bitmap, and the data file. And so I could keep scanning like that. Scan 1, save, save. Scan 2, save, and so on. So it's very quick to do the inspection. I just did about 1 square foot in 2 scans. A little bit less actually because, well, much less because it's 2 inches at the time. So 2 inches, 1 scan. Sorry, I said 1 square foot. That was wrong. So 2 more inches by about a foot of circumference. And another one, there's nothing to be seen in this region. So that is half a square foot, 3 scans. So 6 scans would get you an exact square foot of coverage. 3 scans of 1 foot long each. Now, representing those display colors. So I've got the choice to display the flaws either as depth or represent them as a go, no go. So I'm going to display those flaws as penetrant testing method. So back on my standard, I am actually trying to calibrate the sensitivity in order to have detection of 1 millimeter deep and up. So that's my wide notch. So I get to see the 0.5 mm, the 1 mm, and the 2 mm. So I'm going to just tame the gain down until I get only the 1 millimeter and up to show. All right, that's it. So I've got the wide notch again. Okay, wide notch, 0.5 gets hidden. It doesn't show in red. And then I have the 1 and 2 millimeters. So I can take these new settings basically and scan this piece of pipe and start generating signals that look like a typical penetrant testing. Oops, I forgot some hardware adjustment here. I don't have any readings. Excuse me. Okay, now I'm scanning that pipe again, and we can see that colony, this SCC colony, as I hit it, looking like penetrant testing test. So not all of those flaws are so deep as can be seen. So if I would just increase the gain, I would get a lot more contrast over those flaws. So that can obviously be done live or in post-analysis, post-process analysis. So here's the colony, again, with more contrast. So as I save files or if I freeze the system, it basically gets into analysis mode. This is how you get to review the files. So there's a cursor that appears. So you can take that cursor set and bring it to what seems to be the worst defect here using the 4 controls. And it basically updates the impedance plane with a reading of amplitude and phase, and an adherent operator, or let's say level 2 or analyst, would be able to call that flaw and compare it to the calibration standard. So that's how you would go on a particular defect and look at the depth or look at the signal. But if you wanted to, you could change the representation of those signals and try to either change the gain. So you could change the representation first. I'm going to do a couple things here just to show the post-process analysis capabilities. So this is a different color palette. Whoops, not so different. Let's pick just another one real quick. That would do. Just to simulate a fluorescent penetrant testing. Here we go. So an FPI look of the defects, and then it's possible in post-process to change the gain. So I could hide or show more defects as I change the gain. So it's possible to change the sensitivity as a post-process step. So now I'm just increasing the gain. There's obviously a limit to what we can do by increasing the gain, but it certainly is a valuable tool for reviewing the indications. And if I had a mouse connected on the OmniScan, I could do all sorts of zoom and much faster analysis, which I did not bother doing here for not spending a whole lot of time on analysis on this webinar. So once you're happy with those results, it's possible to go to File menu, get to Report, build a report, and you basically, at the touch of a key, you get an instant report that can be printed, shared, and saved. So that's the screenshot. And now all the editor array parameters, the particulars about the customer, unit number, and all that stuff. And at the end, there's the QA signature and approval part. So again, that can be saved, that can be, and for now, I'm just going to close it. So that was the report capability of the OmniScan emits. There's a last feature that I like showing with that application is called the Alarm C-Scan. It's basically the ability to display the signals as a sharp, clear go-no-go, gray or red signals based on the alarm box that is found in the impedance plane. So that's a more advanced eddy-current representation or eddy-current way of doing the test. If we look at those signals on the impedance plane, you get to see a kind of a blurb, a green signal going up on the impedance plane into the box. So whatever's outside that box would be accepted. Whatever's inside is deep enough, has enough amplitude to be rejected. So we are going to turn the alarm highlighting feature on. So whatever comes into that box will be displayed as red color, and whatever is outside that box will be kept as gray shades. So that makes it a definite, very easy to use feature for accepting or rejecting defects. So again, the gain feature still works, so I can still change my gains. And anyway, the idea is to show that there's a lot of possibilities in this instrument to play with the data once it's been acquired. So that ends the live demonstration. I'm going to go back to the PowerPoint for a few slides before we finish this webinar. Okay, hope you enjoyed that part. We're going to conclude by displaying a couple actual stress corrosion cracking cases, or samples anyway. Starting with this one, those were courtesy of customers that were kind enough to share pictures or various parts of their work with us. So thank you again to those who are concerned. This is concerning a 4 to 6 inch Schedule 10 304 stainless steel recovery line. The insulation was removed. The ECA inspection was performed on accessible areas. The probe employed was a little while ago, so it was an older model, very similar to the kit pipe that we developed recently and released, but it was essentially a almost identical probe, except not as easy to use as the one today. The ECA was used as screening. Then the penetrant testing was used to confirm the indications for the end customers who did not at first believe in a different array, I guess. So they wanted to make sure that it was not black magic too much and it was actually working. So that was the calibration. Made of standard defect depth, made of different defect depths, different orientations, and the method used was kind of a mix between the amplitude sizing that we use today or the go-no-go. It actually, I would call that a rough sizing with two color gradients. Basically, yellowish orange is a small defect, and pink and red are the target flaw that was chosen, which is 50% and up. So it's kind of a go-no-go with a little bit of differentiation. So again, this was one of the numerous examples where there was no flaw detected. And for those who may ask, what is that black bar, horizontal bar on the top? It was one of the coils. So if I go back to the previous slide, during the calibration, it's easily determined with that wide notch that I was showing earlier. It's easily determined whether I have a coil not working, and the OmniScan allows to turn that coil off for inspecting if that happens. So that's what happened there. There was a broken coil on the array. That was an actual crack found, and sorry I did not rotate the picture properly, so the left and the right should match if I would have bothered rotating one of them properly. So that's the same indication. The scan was done time-based, so it makes the signal a little bit less legible too. that's another nicer example of a colony, very severe cracking found, and it was found later to be 50% depth and greater, just like eddy current predicted, or eddy current array. Example 2, well, it's a 14-inch diameter carbon steel pipe. That's the pipe I still have at the back of my chair, and I was showing to you earlier on. That's the same exact pipe. So here it is, some SCC found with the traditional methods, and a close-up on the one of the deepest colony with the with some zoom. And that was one of these scans made earlier on, but we've seen enough during the live demonstration anyway. So the inspection of that half square foot basically took less than 20 seconds, 3 scans, and the penetrant testing in comparison took about 1 hour plus the post cleaning that was not calculated there. ECA provided instant results with imagery. We saved the data. We had encoded scans, a lot more capabilities than the traditional methods. As a conclusion, the SCC, the new SCC Solution, is very easy to use, requires an ECT trained operator, not an ECA trained operator. Good luck finding one anyways. So any ECT operator is now capable of using the OmniScan ECA with the new software. No paint removal is needed. There are several advantages over traditional methods, and there was 2 slides of comparison against each other, so I'm not going to go over that again. There are huge cost savings. It's a lean and green method, ECA. It's using standard OmniScan products and probes. Those probes, everything you saw in this presentation can be ordered today. It's all, some items are on the shelf, some are very quick delivery. Anyway, it's all standard products. And the last but not the least, not to forget the Olympus support. So Olympus is going to be keen on supporting you to start you up with that new solution. We have a lot of documentation, and a lot of it can be found on our website, whether it's promotional documentation or manual style works, instructions and all. If you go to www.olympus-ims.com and you look for flood detectors and OmniScan MX ECA, in particular, I suggest the multimedia tab. We have a promotional video there. We're going to keep adding some training videos pretty soon. So please have a look there. Look for manuals. Look for all kind of information. There's a lot in this section about this new solution and all and other solutions from Olympus. So again, thank you very much for attending this webinar. Thank you for your time today. We look forward to see you soon.
Thank you, Tommy. On behalf of Olympus, I'd like to thank Tommy for his participation in today's event. Thanks very much to all the attendees for joining us. We hope this material was informative and useful. All attendees will receive follow-up emails, all registrants will get follow-up emails, whether you attended or not, with links to the archived presentation. This webinar will be archived on our website at www.olympus-ims.com by early next week. That's going to do it for this session, and thanks again to everyone for participating. We'll see you again next time.